We are group 16 and this is our magnetic levitation system. Introduction to the project. Our goal was to have a relatively lightweight metallic object hover at a distance below the magnetic solenoid. An electromagnetic placed above the object must attract it to balance the gravitational force against the electromagnetic force in such a way that small disturbances do not change the object's position. Based on the position of the object that is determined by a sensor below the electromagnet, we should be able to vary the amount of current through the solenoid so that the distance of the object and the solenoid is constant. The components of our prototype. We made the solenoid using a metal bolt, 2 nuts, 2 washers, and 330 turns of wire. To insulate the solenoids, we would wrap electrical tape around it after every couple of turns. A wooden frame was constructed to support the heavy solenoid. For sensors, an infrared emitter and diode were placed on either side of the solenoid. To support the sensors, a cardboard floor was added. To keep the cardboard in place, push pins were placed on the legs of the wooden frame. This is the second version of our solenoid. This one was wound using a coiling machine to have the wraps tighter around the bolt. Our original solenoid was wrapped by hand and was not strong enough due to non-uniform shape throughout and looseness in the wires. This is also our second attempt at a frame. Our original frame would not support this larger solenoid and did not provide ample room to place the sensors underneath. The cardboard floor was added to support the breadboard as well as the IR LED and photodiode. Our original plan for the sensors was to hang them from the top of the frame, however this proved to be more work than it was worth in practice. For the brains of our prototype, an Arduino Uno was used. Since Arduinos are fragile to voltages higher than 5 volts, a logic level MOSFET was used to prevent the Arduino from being destroyed. A heat sink was attached to the MOSFET to prevent damage from excess heat, as MOSFETs are prone to overheating. We actually experienced this problem quite a few times in our project. Control principle. The IR sensor operates by measuring the light that the photodiode receives. As the object interferes with the IR, the amount of power applied to the solenoid changes. The controller has a positioning spectrum range of 0 to 650. Based on that reading, the controller subtracts ambient light from positioning to gauge if the power needs to be increased or decreased. The spectrum range of our setup was 0 to 450. This was likely due to interference from surrounding light and not perfect alignment of the sensors. Although we were not able to achieve the ideal spectrum range, 0 to 450 was suitable for our needs. Positive values meant the object was going downwards, and negative values meant the object was going upwards. The feedback was then sent back to the Arduino, which controlled the voltage and current to the solenoid. Controller description. Our group used digital control as opposed to analog control. The Arduino Uno with IR and photodiode sensors are shown in the picture. This method allowed for more precise control and more fine-tuning to achieve stability by alteration of the code. Sensor parameters could be seen in Arduino software, allowing for adjustment. Controller code. Pictured here is the code used to run the Levitator. It was uploaded onto the Arduino to work in combination with the circuit that we built. We had to adjust the B value to vary the intensity of the emitter. This increased stability as the emitter provided a better signal to be read by the photodiode and decreased the effects of ambient lighting. Complications. Our initial solenoid was wound using a drill and partially by hand. Unfortunately, it was not wound tight enough and the solenoid was very weak. Furthermore, the number of turns was not recorded, making calculations very difficult. Notable from the picture, the wraps on the solenoid are loose and the shape is not cylindrical as it should be. Due to these complications, we had to exhaust other resources to find a coiling machine and develop our final solenoid. Further complications. We unfortunately burned out MOSFETs by trying to regulate the voltage between the power source and our Arduino. While testing the Levitator, the power was turned on for too long. As mentioned before, MOSFETs are prone to overheating. This resulted in a hole being burned in our Arduino breadboard as pictured here. The MOSFET did not have a heat sink on and therefore melted a large portion. After this setback, we had to relocate the circuit to a different section of the breadboard. Last of major complications. Ambient lighting interfered with the sensor readings. This caused the photodiode readings to be much larger than they should have been. The controller acted very erratic. To remedy this, tape was placed over the sensors to try to minimize surrounding light interference. Although this wasn't the perfect solution, it did assist the controller in getting better readings. Here's the demonstration of our Levitator in action.